Hello everyone, this is the 8th video on the concept of real number. In this video, I will tell you how to use your Euclid's division lemma algorithm to prove some of the questions. So let's start our video. So the first question we are getting here is show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. So let's start solving this one. So first of all, we will take a be any positive integer and b equals to 2. So we have taken a as any positive integer and we have taken b equals to 2 because we need the answer in the form of 2q and the 2q plus 1. Then by using division algorithm, we are well know that remainder is always less than the b. So r is less than b, it means r can be either 0 or 1. Because it must be less than 2, so only two values are possible. Remainder can be 0 or remainder can be 1. So if remainder is 0 and 1, so we can write a in the two different forms. It may be either 2q when remainder is 0 and 2q plus 1 when remainder is 1. Then we know very well when something multiplied by 2, it means this 2q is divisible by the 2. And number which is divisible by 2 is an even number. It means 2q is an even integer. If 2q is even, obviously 2q plus 1 is an odd integer. So by using our division algorithm, we have proved that 2q is the even integer and 2q plus 1 is an odd integer. Same way, we having the next question. Next question says that show that any positive odd integer is in the form of 4q plus 1 or 4q plus 3 where q is some integer. So same way we will take let a be any positive integer. Now we have to express in the form of 4q, so we will take our b as the 4. Same way, using Euclid's division algorithm, we know a in the form of bq plus r and r is always less than the b. It means r can take any value, either 0, 1, 2 or the 3. All the values are less than the 4. After then, if these 4 are the remainders, then a can be in the form of 4q when remainder is 0, 4q plus 1 when remainder is 1, 4q plus 2 when remainder is 2 and 4q plus 3 when remainder is 3. So out of this 4q and 4q plus 2 are obviously divisible by 2. If these are divisible by 2, then these are the even integers. And if these two are the even, then next two are the odd positive integer. So in this way, we have shown that 4q plus 1 and 4q plus 3 are the odd positive integers. Next, we have to show that square of any positive integer is either of the form 3m or 3m plus 1. So in this case, now we have to show the square of the any positive integer. So we start our step same way. Let a be any positive integer because it's a form of 3 3, so we will take our b as the 3. And same way, remainder is less than b always, so r can be 0, 1 or the 2. So a can take any value. It may be 3q for remainder 0, 3q plus 1 for remainder 1 and 3q plus 2 for remainder 2. Now we have to show the square. So one by one in all the three values of the a we will take the square. So case 1, when a is equals to 3q. So we do squaring both sides. So a square equals to 3q whole square. It means 3 square is 9, q square is q square, 9q square. Now we have to show in the form of 3. So we'll take 3 common from this expression. So 3 taken as common. So 3 is left. This will become 3q square. So this complete value can be written as the m. So we get the answer of 3m, where m is 3q square. Every case this value of m get changes, but we get the answer in the form of 3m or the 3m plus 1. Now case second, when a is equals to 3q plus 1. Again we have to show the square, so squaring both sides, we get 3q plus 1 whole square. Here we use the identity a plus b whole square. It's a square plus 2ab plus b square. So a square means 9q square. Solving this one we get 6q and 1 square is 1. Now from these two expressions we can take 3 as the common. So we get 3q square plus 2q plus 1. So this 3q square plus 2q will become m. We get the answer 3m plus 1. Now value of m for this case is 3q square plus 2q. Then case 3, when a is 3q plus 2. Same way, again we'll take the square. So we get 3q plus 2 whole square. Same way using the identity a plus b whole square. A square plus 2ab plus b square. Now we don't need the answer in the form of 4. We need only the form of 1. So we will break 4 as 3 plus 1. So because 3 plus 1 makes our 4. Now from these three terms, we will take 3 as the common. So after taking 3 as the common, we get this 3q square plus 4q plus 1 as the m, and we get our answer in the form of 3m plus 1. So square can be in the form of 3m or in the form of 3m plus 1. Now the next question is, using Euclid's lemma, we have to show that cube of any positive integer is in the form of 9m, 9m plus 1 or 9m plus 8. So now in this question, it may come in your mind to take b as the 9, but we will not take b as the 9 because then we have to solve the expression for 9 times. So we will take b3 here only, because on cubing 3 we can get the value 9 as a common easily. So same way we start our work. Let a be any positive integer and b equals to 3. So remainder is always less than b. So same way remainder are 0, 1 and 2. Then a can be take any value from 3q, 3q plus 1 or 3q plus 2. First case, when a is equals to 3q. Now cube we have to prove. So we'll do cubing both sides. So a cube equals to 3q whole cube. The cube of 3 is 27. So we can easily take 9 out from 27. We get 3q cube. So this will become our 9m. So m in this case is 3q cube. Now case second, when a is equals to 3q plus 1. Again cubing we have to do. So a cube equals to 3q plus 1 whole cube. Now we'll use the identity here, a plus b whole cube. That is a cube plus 3a square b plus 3ab square plus b cube. So this will become 3q whole cube, that is a cube, plus 3a square b plus 3ab square plus b cube. This will become 27q cube. This after solving 27q square. This will become 9q plus 1. So from 1, 2, 3, these three expressions, we can take 9 as the common. We get 3q cube plus 3q square plus q plus 1. So this will become 9m plus 1. M here is 3q cube plus 3q square plus q. So we are getting in the form of 9m plus 1. And the last case, when a is 3q plus 2. Again cubing both sides. So we get 3q plus 2 whole cube. Again we use the identity a plus b whole cube. So a cube plus 3a square b plus 3ab square plus b cube. So solving this one, we get 27q cube plus 54q square plus 36 plus 8. So from first three expressions, we can take 9 as a common. So we get 3q cube plus 6q square plus 4q plus 8. So we are getting here 9m plus 8, where m is 3qq plus 6q plus 4q. So q can be in the form, it may be in the form of 9m or 9m plus 1 or 9m plus 8. So this will prove our question. So hope you are able to understand the concept. Thank you.